All right, here we go. Chapter 2. It's all about one-dimensional motion. All right, one-dimensional motion. There's a lot of types of motion, okay? And what you see in the pictures here are the different types of motion that we're going to try to understand in this class. Now, oh my gosh, you guys are setting up like a religion here. All right, postpone your religion plans until after lecture. All right. All right, so in the upper left, we have linear motion. That's one-dimensional motion in a straight line. We'll be talking about that today. Another type of one-dimensional motion is circular motion, actually. Circular motion can be reduced to one-dimensional motion when you use a different kind of coordinate system. We use polar coordinates, what we call them. Projectile motion is two-dimensional motion, which we will be tackling in the following chapter. And rotational motion is not something we're going to address for a while in this class. In fact, we have to get through a good 2/3 of the class before we address rotational motion. The reason why is because rotational motion contains a lot of aspects that are not necessary to understand the basic ideas of motion. Okay, and I'll say something about that again in a couple minutes here. But here's our goal for today. Real simple goal. Before we attempt to explain or predict motion, which is what we want to do, we want to be able to describe motion, right? That's the first step. You have to be able to properly describe motion if you want to do anything like predict behavior and things like that. So we're going to go about doing that. And one of the ways to do that is with something that's called a motion diagram. A motion diagram is very easy to visualize. It's like watching a video where there's motion taking place and you sort of take a screen grab of your video every 1 second or 2 seconds or whatever. And every time you do that, we consider that a particular frame. And you piece all the frames together into a single image. So there's a car that's driving to the right here. And let's say that car goes at a constant speed. And we take pictures at equal intervals of time. And we'd see the car progressively get to the right. We want to stack all of those into a single image. And that's what our motion diagram is going to be. And if this car is moving at a constant speed, then we can see that the position of the cars are separated by equal intervals of distance. It's because we chose equal intervals of time. So this is an example of that. And by looking at this picture, you automatically can tell what's going on with the car. The car is moving at a constant speed. Okay. Here's examples of other things we can do. This one's fun. Something that's at rest. The motion diagram isn't very exciting. It's just a single picture of a ball on the ground, lonely. It's inanimate, so you don't need to feel sorry for it. But otherwise, this is a very lonely ball. Now, at the bottom here, we have this skateboarder, I guess. And they're moving at a constant speed, which we can tell because we have the pictures equally spaced apart. Okay. The one on the top here shows an object that speeds up. Okay, so we have the sprinter. And what you notice about these images is it's communicating that the person is speeding up because each image shows the runner progressing farther away from the last image. And that is clearly indicating speeding up. The bottom here, we see a car that's slowing down, same deal. As the car moves to the right, the images get closer together. indicating that it's slowing down. And I mean, technically, there's like 4 examples you can have, but obviously, one of them is sort of trivial. So these are the different ways we can explain this kind of motion. If we want to show more complicated motion, like projectile motion, we'd want to draw things that are 2-dimensional. We see the ball being thrown towards the basketball, but when we do it like this, we can see more easily what's happening in the different directions. In the y direction, we can see that the ball slows down as it reaches the peak, and then it comes back down. In the x direction, each image is separated by the same distance in x, and that means the ball is moving at a constant speed in x. So you can combine things into a single image. Okay, having 2-dimensional motion is really just expressing 1 dimension twice, and there's 2 different things going on here. Okay. Now, question for you here. We have 2 motion diagrams of a car. Car A moves to the right, car B moves to the left. They have the same time intervals between photos. Can you tell which car is going slower? Letter in the chat. If you get this wrong, I'm going to kick you out of the Zoom session. We're going to do like that game show. What's that game show? 100 or something, isn't that called 100? So if you get it wrong, you get kicked out. And then the next question, I'll kick you out until there's down to 1 person. And that 1 person will receive their prize for today, which will be a C in the class, which is very generous. So you're welcome. All right, I should look at the chat, I guess, right? A's is A. It's A. Easy peasy, right? Smaller distances between for a given time interval. Right? A is slower, B is faster. So that's another thing you can tell from these images here. Okay, now, look at these cars. What kind of cars are these? These are lame, right? Look at this. Look at this sprinter. I don't care for their shoes. Look at this skateboarder. What a poser, right? All right, so I don't like these pictures very much. So let's get rid of the pictures. Right? Particle model is what we want. We don't want pictures of cars. We don't want pictures of skateboarders in jean shorts. We don't want that. We want simplification. Okay? So we are going to invoke what's called the particle model. And our objects may have a shape and a size to them, but we don't care about the object's shape and size, at least not initially. Not in chapter 1, not in chapter 2. In fact, not until around chapter 12 are we going to care about those things. We have plenty to talk about if we assume our objects are simply particles. No size, no shape. Okay? If you're curious how we would accomplish that, one of the first things we will do in chapter 12 is to work out center of mass problems. And the center of mass is what the particle basically represents. Okay. So now the particle model is good for a couple reasons. One, it gets rid of some unnecessary details like size and shape. We don't care about that right now. The other good part about it is it doesn't require me to draw pictures of cars and people. Okay. Because it's just very embarrassing when we put it that way. Okay. Now, if we use a particle, though, a dot to represent our object, there may be some additional information you may need to include. For example, if I go back to these pictures here, I know car A was moving to the right here because, well, I don't know that, I guess, right? The car could be going backwards, I suppose. Never mind. Okay. The skateboarder. I'm guessing they're not going backwards. They're probably going forward. But with the particle, I can't tell that. So you notice here that we have these points labeled 0, 1, 2, 3, 4. They're meant to be chronologically numbered like that. And I strongly recommend that you do something like this when you create a motion diagram. Okay, here's a motion diagram, incomplete, but still. of a particle of an object, it could be a rocket, that's being launched into space. So you see the points are getting progressively farther apart from each other. And that is communicating that the object is speeding up as it heads upward. Notice that we did make this vertical. We do want to try to represent how the motion looks to some extent, right? So if it's vertical motion, you should show vertical motion. Right? Question for you here. I have 3 different motion diagrams for 3 different scenarios. So spend a bit of time and look over these and put a letter in the chat for what do you think goes with what. Well, let's go. Let's look at B. Let's talk about B. Well, let's talk about these. What's going on with these things? Let's talk about it. Before I show you a letter here. You guys seem to be thinking it's B. I don't know. We'll see. What's going on in A? We have an object that's falling down and speeding up. That sounds like, a ball is dropped from the roof of a building. So I like B. D could be right. What about B? B looks like constant vertical motion, which sounds like something that dust might do. So I'm thinking it is B. All right. And then C is the rocket. I guess the rocket is descending now. Okay, fantastic. All right. Now, let's start, because all this stuff we're talking about here, this is very qualitative. And we're going to slowly transition from having a qualitative description of things into a more quantitative description of things. So let's try to do that. We can throw down a coordinate system in our motion diagram. And we could specify each point as a particular position, right? So if we have this object that's, say, being shot into the air and coming back down, each point separated by half-second intervals, and we have information about where it's located each time. That's nice. You know what you can do with that is you can create a bunch of position vectors. And the way the position vectors are going to look is the tail, every single point can be specified with a vector, right? The tail of the vector will start at the origin because we want everything referenced from the origin, right? So if I draw a position vector for frame number 4, 1, 2, 3, 4, that vector will give me a length and a direction. And that length and direction is how far we are from the starting point and in what direction. And so we can label that R, vector R. So the little vector symbols on top of that. And, you know, that's okay, I guess. I mean, that is put numbers behind this. I mean, every single dot can have a position vector. We can have an R1, an R2, an R3, an R4, and so on. But there is one problem with this. And that is deciding that the origin is where the first ball starts. What if we didn't want to do that? What if we wanted to create an origin somewhere else? Maybe there was another observer watching the ball, and we want to have things centered on them. And well, they're going to have their own position vectors to describe the same object. But the problem is their position vectors are going to have different values for distance and angle, right? Because they have a different origin. So it's a little problematic. In fact, what's a little better to do is to not specify actually position vectors. And instead, we would like to state what the displacement vector is. So you see in the picture here, we have an intersection, 12th Street and Vine, wherever the heck that is. And one person starts on 12th Street and then moves up to this endpoint, which is in the northeast corner, I guess. And both the start and end position have position vectors, R0 and R1. But that's based on the origin here. What I can draw here is going from start to end is a displacement vector, and that's indicated by a delta R, and that indicates the change in the position. And as you can see here, you can do a really simple vector addition. R0 plus the displacement vector equals the new position vector, right? Here's what's nice about delta R, though. it's not coordinate system dependent, right? Say, for example, I wanted to choose, watch, I'm going to annotate this here. Let's go with some red. I'm going to go with a red. Let's go with a thick red. Let's go a little thick. Oh, I got a thick red. Say the origin was right here. Say the origin was up here on Vine, and I can draw a position vector to the start, and I can draw another position vector to the end. So those are two entirely different position vectors, right? They have different distances and different angles, but guess what? The displacement vector is still the same. It still goes from the start to the finish. So no matter what you draw for your origin, your displacement vector never changes. So that's great. Everybody agrees on the displacement vector. And so that's the focus we want to take. Positions are great, but displacement vectors are definitely where it's at, and we're going to stick with that stuff there. And guess what? Position vectors are very easy to draw out. Now, that displacement vector, just to be clear, okay, if I rearrange things, is the difference between the two position vectors, right? R final minus R initial, whatever those are. So it's a vector subtraction that helps us get that. And we should now be well versed with vector subtraction. You just did the homework. We recently went over that. I'll say a little bit more about it here, but the way we do vector subtraction is you take that second vector and you rewrite it. So it looks like plus a minus R sub I. So it's really like a vector addition where you flip that second vector around. Okay. Now, also about this is we have to also consider our delta t's. We have to consider our time intervals. Fortunately, though, time is a scalar, right? It's not a vector quantity. And so manipulating vectors with scalars is very simple. It's just a multiplication. And we are free to choose any time interval we want. And because of that, we can make our lives easier and always choose one second or one something. So we don't have to really think a lot about the time stuff there. But they do have to be equal velocity. So remember, we're describing motion here. We got the position stuff down. Now we want to tackle a velocity vector. But guess what? Velocity vectors, super easy, because the definition of velocity is the following here. The velocity vector, its definition is the rate of change in position, right? Or really, it's really displacement is what we're talking about here. And so it's a simple ratio. Delta R vector divided by delta t is your average velocity vector. Is your average velocity vector. Okay. Now, let's go back here. Let me go back to these pictures. Okay, look. It's very easy to draw displacement vectors. Very easy, right? I mean, it's like connecting the dots, right? And the fact that we can take a concept and turn it into a kindergarten exercise is so cool. Very cool. Let me draw your displacement vectors right here. That's one displacement vector. That's two displacement vectors. There's a third one. Here's my displacement vectors. So pretty. Right? Now, it's very easy. That's it. I don't even have to have a coordinate system. I can just draw these lines. Now, what is... Now, if I go now to my velocity vector definition, I don't know how to use the scroll on my mouse, apparently. There we go. Look at the definition. Strictly, what is the velocity vector? The velocity vector is equal to the displacement vector divided by time, which is a scalar. And I can choose the time interval to be anything I want. So let's choose 1 second. And if I do that, we see that the displacement vector and the average velocity vector are identical. So here, is a very simple motion diagram of two animals. We have a hare, which is a type of rabbit. I read about those when I was a child. And they're showing velocity vectors. Now, those are displacement vectors too. I mean, you're drawing from one point to the next. But we can turn those into velocity vectors. So guess what we're going to do now? We don't need to write the displacement vectors. We can just draw out the velocity vectors. And that explains both. That's a beautiful thing. Okay. So here's the hare. Here's the tortoise. The hare has a much higher speed. So the length of the velocity vector is longer to indicate the higher speed. And each point is separated by equal intervals of distance. So we know that the hare is going at a constant speed. Tortoise is the same deal. Tortoise is a little slower. Okay. So that, and now notice too, I've stopped labeling my points with numbers because now I can label my velocity vectors with numbers. V0, V1, V2, and so on. Okay. So this here is a very nice way to describe the race between the hare and the tortoise. It's a really good description. There's a lot of information that's being communicated here, actually. Okay. So let me draw out a motion diagram for this particular motion here. A skier starts and rests at the top of a 30-degree snow-covered slope and steadily speeds up as she skis to the bottom. When she reaches the bottom, she glides along a smooth horizontal track. Create a motion diagram to represent this. All right, so let's look at this. This is a slightly more complicated example. Okay, so here's the picture of it. Now, this motion, there's actually two different kinds of motion happening here. So you need to be aware of that. When you read the problem, we can tell that you can break this up into two problems. There is going down the incline, where we speed up, and then when we hit the bottom, we're moving along at a constant speed. So you have to make sure you illustrate both of those, and they properly reference each other. So I'm going to draw a little line here to represent the two different types of motion. There's the stuff on the left, which is speeding up, and the stuff on the right. Okay, so what am I doing here? Well, I have decided to use 1, 2, 3, 4, 5 points to represent the motion down the incline. And when you go ahead and draw motion diagrams yourself to represent motion, my recommendation to you is between 4 and 5 points for each type of motion that you work with. Okay, you don't want to do less because you don't want to create any ambiguity in what you're doing, and more points doesn't usually result in additional information. So 4 to 5 is kind of the sweet spot, and that's what I recommend you shoot towards. So I drew my dots here. I'm going to zoom in a little bit so you can see this a bit easier. Okay, and I'm going to move this, I guess. So I draw 5 points. I draw velocity vectors that connect the points. I call this V1, V2, V3, and V4. Okay. Now there are little accelerations here, and I'll come back to this example to explain those. I haven't talked about acceleration yet. I'll explain those later. But this is good. It's the vectors are labeled. I have enough points. I'm showing motion down an incline, which is what the motion's doing. And notice the velocity vector lengths. You want to make sure that you're clearly communicating that the object is speeding up. So each vector should be sufficiently longer than the previous one, and that will properly communicate speeding up. Now we reach the bottom. So I've used 4 points to illustrate the bottom. Okay, one of the points is the point from before, and then I have 3 additional points. Now it says smooth horizontal track. Now that word smooth is code word. And unfortunately or not, I don't know if this is unfortunate or not, there's a lot of code words in physics. A lot of words that seem innocuous, but actually are trying to communicate something that's a little bit more meaningful. The word smooth is meant to mean frictionless, which is also meant to mean that objects should be moving at constant speeds on those surfaces. So when you see smooth horizontal track, the translation is we're moving at a constant speed. Okay. So you want to show vectors that are equal in length to illustrate constant speed. The points have got to be equally spaced. I used V5 to represent the vector, and I drew all of them as V5s to indicate they're all the same vectors. And the last detail here is this vector is longer than all the previous vectors. It wouldn't make sense to draw it shorter because that would indicate that somehow it's slowed down, which there's nothing in the problem to indicate that it's slowed down when it transitioned to the horizontal track. So you don't want to include any extraneous information if we don't know for certain that that happened. I mean, it's possible, but nothing really indicated that, so I'm not going to do that. And this is a near complete motion diagram. In fact, actually, it is a complete motion diagram with the acceleration vectors drawn in there. And I'll explain those in a minute here. Is there any initial questions about this picture?
Yes, Professor. So I have a question about the vectors, like how you wrote all of them as vector 5.
Yes.
So is it because they are the same length? Or
Yeah, I decided to do this. Now, I think if you read in your textbook, they won't do this actually. They actually label them differently, which is not wrong. I label them the same so I can better communicate that the speed is a constant speed and that these vectors are identical to each other. So remember, vectors are identical if they have the same length and the same direction. Doesn't matter what their position is.
So would it just basically what you're saying is like vector 5 times 3 then?
Yeah, but times 3, there's nothing really times 3 about this. I happen to choose 3 vectors here. I could have chose 4 or 5. The important thing here is that you're drawing equal vectors. They have the same length and direction.
Got it.
Yes. Okay. Any other questions? Okay. Great. Yes.
Is the 30 degrees even important for this story, or?
Not for the motion diagram. The only thing about the 30 degrees is you should show something that's sloped. But 30 degrees does not play into the problem. Once we put numbers behind this and we actually have to solve something, the 30 degrees will then become important. But this, for the moment, is very qualitative in nature.
Okay.
And
Thank you.
to be clear, too, like, is this exactly 30 degrees? I don't know. Does it look like it's 30 degrees? Yes. That's sufficient. That's it. Does it look like these things are speeding up? Yes. Are these vector lengths exactly to scale? I don't know. Is that important? Not really. See, this description, you have to be able to look at this picture and be like, yeah, that description is being illustrated correctly here. By the way, there's a lot of details that were not included that we don't need to include. What was the skier's beanie's color? Was it red or blue? I don't know. Not important. A lot of things not important. So we'll never know about the beanie. Or if they even wore a beanie. Maybe they wore a helmet. People get hurt, you know. Helmet's a better idea. Doesn't not as fashionable. You could wear both, I guess. A helmet with a beanie on the outside. Or the other way around. There's so many different things. Okay, that's not physics though, so let me not do that then. Let's go back to my slides. Yeah, now let's talk about acceleration. Acceleration is a little tricky, but it's the good stuff. It's good stuff. Not as easy as the other things. The definition of acceleration is the rate of change of velocity. So it's a ratio of a change in velocity vector divided by delta t. Now here's why it's a little tricky, because it requires you to do a vector subtraction on the velocity vectors. That's a little more challenging, right? A little more challenging to do. So here's how you would do it though. And this is just simple vector subtraction. So you're not necessarily learning anything new today. This is more of like, hey, do you remember this? Say these are our two velocity vectors. And you can see here that clearly the object is speeding up because the second vector is a little longer. So now the vector subtraction would be the Vn plus 1. That's what we call the first vector. The Vn is what we call the second vector. That's the order in which they appear in the subtraction. But the way we do this is we have to write it as plus minus Vn. So we draw the first vector out, Vn plus 1. Take the second vector and we flip it and we attach it to the front of vector 1, which I did right here. And then you connect from the tail of the first vector to the tip of the second, which is done right here. So this represents my delta V vector right there, delta V vector. Now, the acceleration is equal to delta V over delta T. But remember, delta T can be anything we want, so we'll just make it equal to 1 second. And your delta V vector is effectively the same as the acceleration vector, which I can now draw at this intermediate point. I'm drawing an acceleration vector here, indicating that that is the direction of the acceleration, and that means things are speeding up here as we move along. And the acceleration vector, its direction really matters, but its length does not matter. Do not worry about the lengths for acceleration vectors. They're not important. Again, it's a detail that doesn't really matter. All we care about for these things is, are we speeding up or are we slowing down? We don't really care about that particular numerical rate. That's not important for this. Okay. So if I go back to my original picture, I can throw in now my acceleration vectors. And let me just give an example of how I would draw one. Okay, so look at vector 3 and vector 4 here in the picture. Screen sharing, I'm screen sharing. So let's do this. So to figure out the acceleration between 3 and 4, okay, you draw out vector 4 is already drawn out, obviously. Let me draw vector 3 flipped over. If I flip a vector 3 around, it's going to look like that, basically. And so if I draw this and say green now, this is my delta V, which is also my acceleration. So I drew a little acceleration vector under my point, and I labeled it A. And you can see that I have an acceleration vector for every intermediate point. So you draw them at intermediate points. Okay, between vector 1 and 2, there's an acceleration vector. Between 2 and 3, between 3 and 4. Okay, now in the constant motion part, it's constant speed. So you don't have to draw acceleration vectors. I just put A equals 0. Okay, now vector 4 and 5 are a little bit funny, I guess you'd say, because they do change direction at some point. So let's do the vector subtraction there. Okay, vector 5 is left alone. Just leave it like that. I'm going to flip vector 4 around and redraw it, which would be something like probably this. Yeah, about like that. That's pretty much vector 4 flipped around. And then in green, I'll draw the delta V. The delta V would be up like this. So that's my acceleration vector, actually. It's going up like that. That's why I drew it down here like that. It kind of goes up, because what has to happen here is there is a component in the x direction still. So the object still speeds up a little bit in this interval, but now there's a velocity that's directed upward that cancels out with the downward, so we have a nice horizontal motion here. So that's the purpose of this acceleration vector. Speeds us up a little bit and eliminates the vertical motion that was taking place. So That's probably the only thing that's really challenging about these diagrams is trying to really properly see what the acceleration vectors look like. But you just got to follow the vector subtraction rules. The reason why the acceleration vectors are so important is because that really dictates what's going on with the motion, right? Constant motion is not very interesting. It's just constant, right? But accelerations are very interesting. And when we get into Newton's laws later, Newton's laws, they're all about acceleration. So we have to be able to really see the acceleration well. Any questions about the acceleration vectors? I mean, you'll see more examples, but any initial questions on that? Question for you. A particle has a velocity v1 as it accelerates from 1 to 2. What would the velocity vector be as it moves away from point 2 on its way to point 3? So point 3 is somewhere further down. So with this initial velocity vector and this acceleration vector, what do you think the next vector should look like? What do you think? So again, what I was saying here is I'm going to draw a vector after 2. But what should it look like? So give me a letter here. Let's see. I got a whole lot of B in here. And I would say E. What the heck? Classy right now. All right. B is, I would say B is probably the most correct. Okay, because what's happening here? We have velocity vector downward. We have an acceleration vector that points in the opposite direction. That means slowing down. That means slowing down. So velocity vector 2 would have to be on here, and it'd have to be shorter. Right, shorter. So if I draw that, it would look like this. Like that, a little shorter. Okay, and again, you can see how that's going to work, because if you keep vector 2 the same, when you redraw 1, you're going to flip it around, and it's going to look like that. Something like that, when you flip vector 1 around. And so the remaining portion is the acceleration, so it points upward, right? And that's just classic slowing down. When your velocity and acceleration vectors point in the opposite direction, you're slowing down. Okay. Now, A is wrong, right? A is just wrong because A indicates speeding up and the acceleration vector doesn't work. What about C and D? I'll tell you what, C and D are not technically wrong because this acceleration vector has a somewhat arbitrary length to it. I mean, it's possible the acceleration vector was extreme. It was like an enormous acceleration, and that actually might cause the particle to not just slow down, but to change direction. So one could argue that C and D could be correct. Although you definitely don't want to choose those over B. B seems to be what is intended here. All right. Now, let's look at a two-dimensional thing here. A particle undergoes an acceleration while moving from point 1 to point 2. Which of the choices shows the velocity vector as the object moves away from point 2? So, what's the second vector going to look like here? What do you think? Yeah, I mean, I will say this. The vector subtraction is like your last resort on trying to figure out the directions for things. After you see several examples, you'll sort of get an intuitive sense of how to do it. That's the hope. But you could always fall back on the vector subtraction to verify, right? If you think you've got the correct vector in the list of things here, you can do the vector subtraction and see if you get A as your thing. Everybody seems to think it's C. And I think I might agree with you that it's C. It is C. Well, let's go through the other ones and determine why they're wrong. Now, one thing that's good to do, especially when you have vectors in 2 dimensions, is you got to keep track of what's going on in X and Y. Vector 1, the velocity vector 1, is only an X component, right? And our acceleration vector only has a Y component. So when this acceleration vector is applied, it will not change the x direction motion at all. It will instead introduce a y component to the velocity vector. So we would expect the vector to now point down and to the left. And so A doesn't work because A now shows an upward velocity, which the acceleration is not doing. B is like, I don't care about the acceleration, I'm going to ignore it, which you can't do that. And then D doesn't make sense because D somehow eliminates the x direction motion. But there's no acceleration that we can see that does that. C works. C still contains the x direction velocity, but now shows some y direction velocity that's downward. So C is good. Okay. So here's another example of the motion diagrams. This one is for a very similar example where a skier glides along a smooth horizontal slope and then speeds up going down a hill. These are a very similar situation to what I had before. These shows the vector subtractions here, so you're very clear about what the acceleration should look like. But there's 4 points drawn for the smooth motion, and velocity vectors are indicated there, and they put acceleration as 0. They show a 0 vector at each intermediate point. There are 4 vectors for down the incline. We can see clearly we are speeding up. All these vectors are larger than the original vectors. You can actually see the vector subtraction performed down here, demonstrating why the acceleration has to point downward. But you can generally use this following rule. If you're trying to illustrate motion where things speed up, then the acceleration and velocity vectors go together. And if you're slowing down, they are opposite directions. You'll see that from the vector subtraction, but it's a general rule that always applies. Okay. So, now, I have put a little coordinate system down here for x. Okay. Oh, this is just what I was saying, actually. So the picture at the bottom right here, the one on the top, is showing speeding up. Velocity acceleration vectors in the same direction. When the velocity and acceleration vectors are in opposite directions, then you are slowing down. In fact, that is exactly what is meant by speeding up and slowing down. Okay? Yes, we know speeding up means you go faster. Fine. But from this motion diagram vector standpoint, that's how you ultimately will know if an object speeds up or slows down. What are the acceleration and velocity vectors doing? Are they together or are they opposite? And that's it. Okay, that's speeding up and slowing down. Okay. Okay, now, one other thing I want to mention here, and I probably will not follow this myself, so I'll work on it just as much as you work on it. Because of some of the things we're introducing here, you want to make sure you're very clear about the language that you're using. You want to use the phrases speeding up and slowing down, okay? As opposed to saying accelerating or decelerating, okay? As far as you should be concerned, the word deceleration doesn't exist. It doesn't exist, okay? Because deceleration a lot of times is meant to mean slowing down. But that is, you know, on a strictly physics definitions of things, both speeding up and slowing down is acceleration. Acceleration just means change in speed. Doesn't mean faster, doesn't mean slower. So we're going to try to stick with the terminology here. Acceleration should refer to any change in speed, whether it's speeding up or slowing down. If you need to indicate speeding up or slowing down, do that. Same thing with negative signs and positive signs. Right? Look at these vectors here. Vector, well, actually, here we go. Actually, this is the next slide. I am so happy that my thought process and these slides are working together. That means years ago when I made this, and today I'm in sync with myself. So it makes me very happy because dementia will set in at some point, but not yet. So I'm very happy about that. Anyway, so the signs of things for position, velocity, acceleration. If there's a coordinate system placed down, or you need to place a coordinate system down, this will determine if your objects have a positive or negative position. You need to define an origin somewhere, and notice my axis here. There's a little X on the right. And that X there is not just a label, it is to tell you which direction is positive. Now, I know in math classes you're very used to right being positive and left being negative. That won't always be the case. There may be situations where we want left as negative. Okay? Usually up is positive, down is negative. There's a lot of situations where you want down to be positive. So you got to be very clear when you do your problems to communicate which direction's what. Okay? So the axis drawn here is meant to indicate right is positive. So that's a positive position, that's a negative position. Velocity vectors, which by the way would be the same as the displacement vectors. This velocity is to the right. It's positive. Okay? Why is it positive? It points to the right. This velocity is negative because it points to the left. Great. Acceleration. This object is accelerating to the right. The acceleration is positive. This acceleration points to the left and it's negative. Now, is our object speeding up or slowing down? We have no idea. There is not enough information in this little table here or whatever to tell that. When you have an acceleration that's positive, what does that mean? It means the acceleration points in the positive direction. It does not mean the object speeds up or slows down. This acceleration is negative. What does that mean? It means that the acceleration points to the left. It does not mean it's slowing up. Slowing up? Does that mean it's speeding up or slowing down? Slowing up. Slowing up. Sounds like some kind of slang. All right, slowing up. Man, you slowing up right now. I don't know how to use that appropriately. I'll think about it. Here's how things would look in the y direction. I have a y-axis defined. Positive is up, just because I happen to say that in this situation. It might be different in other situations, but the same thing applies. If the vectors point up, they're positive. If they point down, they're negative. Do we know if they're speeding up or slowing down? No, we do not. We don't know that. All right. So, in summary here, the sign of position tells you where the object is located. The sign of the velocity tells you which direction it moves. The sign of the acceleration tells you which way the acceleration vector points, not if the acceleration is speeding up or slowing down. How do you know if you're speeding up or slowing down? The way you know is you compare your acceleration and your velocity vectors together. That's how you know. Okay? So, let's go back here. See these two acceleration vectors right here, velocity and acceleration vector? Let me circle them. If this was my acceleration and velocity vector, I would be speeding up, right? What about the other case? What about this one? What's going on here? Speeding up. Speeding up. Now, what if I were to compare this vector with this acceleration vector? Those point in opposite directions, so we're slowing down. Okay. We're slowing down. Not slowing up. It could be speeding down, but we're not going to do that either. All right. I'm going to test you now. Motion diagram shows a particle that is slowing down. The sign of the position and the sign of the velocity are what? What is the position? What is the velocity? A lot of people saying B, and I think I like B, because B is right. Our positions are to the right of the origin. We've called right positive, positions are positive. The velocity vectors point to the left, they are negative. Now, we're not talking about acceleration here, but here the acceleration is positive, and that means this object is slowing down. Great. Here's a motion diagram of a car that speeds up on a straight road? You tell me. What's the sign of the acceleration? I don't have acceleration vectors here, but if I want to put them in, what would be the sign of the acceleration? All right, that was a stretch for the ages. B's and A's and B's and A's. I don't know, man. I don't know. A lot more B's, though. That's good, because B is right. B is right. It's negative. Why? Because the accelerations point to the left. So here's the acceleration vector here. I'm going to draw my acceleration vectors there, 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 and here. There you go. That's my acceleration vectors. I draw little A's if I could, but I don't want to attempt to do that. But
Professor,
yes,
I actually have a quick question.
yes.
So for position, does that make it also negative or would that make it positive?
No, position here is positive. Velocity is negative. Acceleration negative.
All right, then if the green arrows were pointing the opposite way for position, would that be negative?
Well, you don't look at the arrows for position. You just look at where the points are relative to the origin. We've called the right-hand side positive, and all the points lie to the right, so they're all positive.
Okay.
The object is traveling to the left, so even though its position is positive, the velocity is negative because it must move into the left. And then the acceleration also.
Okay. Thank you.
Sure. Any other questions about this? All right, so let me just say it one last time. The car is speeding up. That does not mean its acceleration is positive. Okay? The acceleration is whatever sign the vector, whatever direction the vector points. The vector happens to point to the left, then it's negative. So you can have a car speeding up with a positive acceleration, and you can have a car speeding up with a negative acceleration. It all matters what the velocity is. Okay. Fan. Great.
So real quick, just to be clear, velocity, so you can have a negative velocity, whether it's positive or negative depends entirely on the direction in relation to the origin.
No, it just, well, sort of. I mean, the velocity vector, it's whatever direction it points, period. It's not, it hasn't really nothing to do with an origin. I mean, other than the origin kind of tells you which direction is positive or negative. In this case, left is negative, right's positive. And the velocity vector is negative because it points left. That's it. Just because how it points. So.
Got it. Okay.
Yeah. Got to remember here, the actual position of a vector is irrelevant. Okay, the actual position of the vector is irrelevant for the motion. I mean, if anything, it only tells us really one thing, that we are positioned over here, but you know that vector is negative no matter where it's put. Right? No matter where it's put. All right. Let's keep going, I guess. All right. Any other questions? I am recording. I got too much banter today, so I'm going to have to edit a bunch. I don't like to put the banter in. I don't like the banter. All right. Okay, let's do another problem here. A ball is tossed straight up in the air. At its very highest point, the ball's acceleration vector would be what? We had, oh my goodness, we got some B's coming in pretty hard. People are coming in really hard with these B's. What else? Yeah, you know, I got a C in here. I got another C. Oh, now the C's are rolling in. Uh-oh. 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 Got B's and C's. Well, I think we're pretty certain it's not A, right? Guess it's not A. The answer here is C. Yeah. Now, here is a really detailed description of what's happening here. I throw a ball into the air, right? Here is the path as it goes up. Velocity vector, velocity vector. Getting shorter, indicating that acceleration is downward. At the highest point, it stops instantaneously, and then it starts to fall. So here's the next vector, and the next vector, and the next vector, and then we can see we're speeding up. But at every moment, the acceleration never changes. If it points down beforehand and points down afterwards, well, it has to be pointing down at that one instantaneous moment. In fact, the acceleration acts to slow the object down, and then when we get to the top, it acts to flip the direction of the object, and it speeds up as it comes back down. Okay, so the acceleration is definitely not zero. If it was zero at the top, the ball wouldn't move. It would just fly up into the air and just stay there. So the velocity is zero, though. No, the velocity is zero, but the acceleration is not, and it has to be non-zero in order for the direction to flip. Okay. So this is a really nice question, but you know, you'd have to draw things out, right? And then you look at these two vectors. This is the last upward vector and the last downward vector. Well, if you do a vector subtraction there, you're not getting zero. Look, you can see the vector subtraction up here. So definitely there is still an acceleration there.
I got an interesting one.
Yeah?
So what about a balloon? You let it go up into the atmosphere. It has an acceleration upwards,
Yeah.
but then once it reaches equilibrium, it just stays there.
You're right. So if we were to draw now, so you're talking about a balloon here. If you know, I mean, if we're talking just about velocity and acceleration vectors, if the balloon is speeding up, you would have to show, you know, ultimately a net acceleration that's upward. And we just have to realize that that is multiple things involved, right? If a balloon is accelerating upward, well, that means gravity still exists, obviously, right? So there is an acceleration downward due to gravity, but apparently the upward push from the air provides a larger acceleration. But all these acceleration vectors, to be very clear, are net acceleration vectors. So if there's multiple things that cause the object to accelerate, we don't care about that at the moment. We just want to know what the net acceleration is. We'll worry about the accelerations and their details in a few chapters. For now.
Got it. Okay,
Yeah.
so even in this example, there are multiple accelerations. For example, the downward acceleration that's displayed is gravity, I'm assuming.
Yeah.
And then in the beginning, the upward acceleration is going to be the person throwing the ball up.
No.
No?
In fact, we're not showing the person throwing the ball. That's not being illustrated here. We are looking at the motion the moment the ball has left the hand, because there's nothing down here. We're not indicating the actual toss. Just to be clear, yeah, this is referring to once the ball leaves the hand, we want to see what's going on here.
Got it.
Okay, I think your dad is hanging out with my dad, Shelby. That's the only thing I could think of. Yeah. It's been about 20 years, but you know. And I moved a bunch. So, never know. Okay. It's okay. All right. We're all okay. No, we're not. This is pandemic. This is terrible. Okay. All right. After this, I'm going to do a good cry in the shower. Love a good shower cry. Yeah. Well, I think he was gonna build the grocery store. I think that's why it's taken 20 years. I think he's building it. I don't really know. Whatever, it's fine. Okay. So one last example. One last example here. Okay. Let's look at the last example here. Draw a complete motion diagram for the following situation. A roof tile falls straight down from a 2-story building. It lands in the swimming pool and settles gently to the bottom. Okay. So there is 2 parts to the motion here. There is the falling from the roof, and then we hit the water and we settle gently. So when the tile falls from the roof, we are going to experience an acceleration. So I have 1, 2, 3, 4, 5 points drawn with progressively longer and longer velocity vectors. I've labeled them V1, V2, V3, and V4. We are speeding up, so I draw acceleration vectors at each intermediate point. Now, I took a little liberty with the second part. It lands in a swimming pool. Well, generally speaking, if an object hits the water, it will at least temporarily experience a pretty significant acceleration that slows it down. So the very next vector I drew that shows it in the water is showing that the velocity is a bit shorter now, because I'm assuming that the water did slow us down a bit. And so I have an acceleration vector here that points upward, indicating that we slowed down a little bit. Now, that's not explicitly stated in the problem, but it's a very reasonable assumption to make because that's just how things work. So, a reasonable assumption is you can justify yourself is fine. You got to understand that, and one thing you're not going to like about this course is there's a natural ambiguity in our problems. And unfortunately, you have to make a lot of simplifications, justifications for things. As long as you can form reasonable arguments, anything goes. Did I have to include the acceleration vector here? No. Doesn't make it wrong. I think it's better to have it in there, but there's nothing explicitly wrong if you don't have it. It's strange, but it's possible. I mean, there can be objects that are, sufficiently, like if it was a rock, right? I mean, the rock's not going to have much of a slowing down. I almost said it. Not going to slow down too much when it hits the water. So you can ignore that detail if you don't think it's significant. But a roof tile, yeah, I think maybe they're a little light. Anyway, you hit the water and settles gently to the bottom. That's code word for constant motion. So I'm going to show constant motion in the water. I have a bunch of points here. I label all the velocities the same, and I say the acceleration 0. This is completely reasonable. Is this the only answer? No, but it's a good one. You can make some arguments about this thing here. And if you wanted to throw, don't do that. I was going to think, can you make this harder? I guess you could, but don't do that. That's weird. So don't do that. Okay. So